All right, so we start today by showing you another integration by parts problem. What would you like to let u be? See how your intuitions are on this. Go through your list. And actually, I think I mentioned on Thursday when we were doing this class that it actually doesn't matter. The e and the t, exponential versus trig at the end, doesn't actually matter. I think you'll find you'll have the same kind of feeling on this problem, whichever you choose. But we'll obey the limit instructions. We'll let u be e to the x. Yeah, I think that's a fun way to do this. Exponential before trig. We said that, but like I said, I promised you would have great success. Notice, I mean, kind of the thing too about the reason we pick what we pick. Notice that in both cases, you will be able to infinitely differentiate or integrate either one of these things, right? Like, is it hard to integrate e to the x? No. Is it hard to differentiate it? No. Is it hard to integrate or differentiate cosine? No. And so really, in the end, either choice will be great. And neither of them ever goes away. I mean, that's one of the reasons we pick polynomials, is like at the beginning, because eventually you have like x sine x. You know that differentiating x makes it 1, and we like that, you know. But that's not going to happen either. So you could really be pretty flexible here and have success. With a pretty big footnote. I think you're about to see something that you're not going to like at first. Certainly the differentiation and the integration here is easy. Everything is going just peachy. What is that, sine x? Yay! All right, so what do we get? UV minus the integral of v du. Stop us if you have a question about one of these so far. Yeah, now of course the problem you see is that the integral we have over here, keep in mind our discussion from really earlier when we were asking like, is this really working for us? The question was like, the question is always, is this integral an integral we can do? And we haven't really made any it's clearly just as difficult as the integral we started with. But I suggest that we press forward anyway, just for fun. Let's try and apply the same technique. We'll use integration by parts again. This time we'll let u be e to the x again. We're working on that integral over there, just that one piece, right? uv minus the integral v du. All right, so let's do the same thing. Run through this here. Go ahead. You do it too. This time dv will be, if this lasts forever, it'll be a fun forever, won't it? No. You and me taking derivatives of exponential and trig functions together forever. It'll be beautiful. That sounds like a wonderful forever. We could just do this all day. V equals negative cosine. Is that what I have to say? Come on, check me on all this. Okay. So here we go. Negative e to the x. Careful of all your signs here. Cosine x minus the integral of, how about plus, yeah, e to the x cosine x dx. Check me on the signs there. Let's just take a moment to breathe and look at this and make sure that this is perhaps not helpful, but correct.
Why plus?
I did minus v du. No, I haven't done anything with this minus out here yet. I don't know. You do your own bookkeeping and tell me how you come out.
It's 2018.
All right. So, all right, let's take another second to pause. Everything okay there? I want to make sure everyone is okay with all parentheses, the negatives, the 2u substitutions. There's a lot going on here.
It's like next to mine.
And now we still need to back away and be like, okay, I'm with you, Mr. Chase. I think I've checked all your signs, and I think it looks good. But I'm still not sure I'm with you in terms of like why anyone would continue doing this. It sounds like we're going to do u substitution again. But what I want you to do is back away and just stare at what we're doing for a second. Look at the whole equation, if you will. What do we have? We have this thing that we don't know. This is an unknown. Let's call it capital I for integral. This thing, capital I, is equal to this minus this plus capital I. Do you see it? Say it again. Up here? So say it again. Which part? V is the antiderivative of this here. So here we differentiate over here in this column. Here we integrate. Yeah. All right, so let's just make it, let's put a real fine point on it here. What do we have right now? We have this on the left, sorry, dx, equals, and let's actually try and get some of those minuses in parentheses to be resolved too. On the right is equal to e to the x sine x plus e to the x cosine x minus, I guess, the integral of e to the x cosine x dx.
No way.
All right, so let's just say it again with the i's. What's our equation we're looking for? The thing we'd like to know in the end is what is the value of I, where by capital I mean this. So what are we looking at? We're looking at the equation I equals e to the sine x plus e to the cosine x minus I. What would you do if you were solving for the letter I? Yeah, basic algebra. You would take minus I, add I to both sides, so that you get two of these. Notice how close we are. You can taste it.
Wait, you just divided by 2?
We are going to divide by 2. I haven't done that yet. So we thought we would do this forever, but it looks like we're done. Please, as usual, check the derivative here. I don't think it'll take long to do. I'll just give everyone a second. You might want to write it on a paper or something. Check it quick. Actually work it out. Make sure it works. Okay? I'll do it too. We'll all do it together here. Just silently give everyone some space, some mathematical space.
Amber, I got you a Christmas present. How are you? It's 4 mushed grapes.
Stop talking. We need psychological space. Just want to make sure that it's right. 1/2. Franklin, I'm thinking. All right, so I get all right. All right, did you check it? Did I give you enough time to check it? Take another second if you need to, but I'm feeling really good about it. I just checked it and it's right. You get a 1/2 e to the x cosine x and then another 1/2 e to the x cosine x. You add them together. It's beautiful. So this technique is called, as it says up on the top, which you probably didn't pay attention to when we started the problem. This technique is called solving for the unknown integral. You've experienced it, and that's, there you go. You've had the experience. Good job. All right. Now, second integration by part, the special case, fun, extra piece for integration by parts, is a method called tabular. You're really going to like this. I stole this, if you have your notes carefully constructed in your notebook. You'll remember this example. It's very similar to number 29, too. It's like one of those ones where we're going to need to use substitution twice. We've developed this before. It's the same problem we did at the end of class on Thursday. Do you see it in your notes? Do you see it? Yes. So you already have the answer in front of you. I just want to present this tabular method as a very quick, very nice way of organizing our work. Okay. Amy, can you stop playing Monopoly? All right. The way we choose f and its derivatives is the same. I want you to think of this as u, and this is dv over here. Okay, so we're choosing f and its derivatives with the same criteria you use for Lipit, right? So you're putting x squared here. That's what our u is going to be, and over here we're putting the other function. We're going to omit the dx, but this is the thing. We're going to integrate along this column. We're going to differentiate along this column. Here come the derivatives of x squared until we hit 0. Okay. This technique works when you have something that differentiates in a finite number of steps to 0, like this. Huh? What's wrong?
No, it's not okay.
Leave the column heading for g of x.
And it's integrals. We're going to integrate this. Okay, fine. You win this time. All right, its integrals are easy. There we go. All right, and then here's what we do, and you can go back and see where this works. I mean, think about the way we keep track of parentheses. Notice that every time we get like the opposite sign here, right? It's going to be a minus, but then this is actually going to end up being a plus. So if you put a plus here, and a minus here, and a plus here, and again, this is just a way of organizing your work. And then connect diagonally this thing times this thing times this thing times this, plus c. That's your antiderivative. Okay?
Wait, why is it negative? Why is it negative?
Like I said, you're the one that did this over here, Derek, so you felt this, right? You're like, minus here? No, it's okay. I just want to make sure you see it. Like, does this end up being a minus here? The answer is no. And if you were to do integration, imagine you had to do integration by parts 3 times. Now you'd have this expanded into a uv minus v du, and that really would be a minus, because you'd have a minus, and then another minus, right? So that's why every time you do another integration by parts, you flip the sign again, right? Because if you do nested integration by parts, that negative in front of the integral becomes a positive. Oh wait, no, a negative, then a positive, right? Depending on how many layers deep you are. So compare this, guys, with the answer we got from yesterday. Are we right? Let's review what we just did, okay? So use Lipit to choose the first column entry, the thing that is choose f, the thing you're going to be taking derivatives of, and g, so just like u and dv, right? Make a 2-column table, write down the derivatives here, the integrals here. I got myself color-coded, okay? And then alternatively label the columns starting with a plus, minus, plus, all the way down the column, and then diagonally multiply. You're not going to use this first entry. And this is just, like I said, not anything different. In fact, this is a technique you will never need in your life. You can just do repeated integration by parts if you like. It's just a way of organizing your work really, really nicely, right? But I think you will like it in terms of bookkeeping when we get, I'll pull this back up in a second, when we get to like this problem, for example, or this problem. Right, really? You're going to do integration by parts 4 times? All right, we'll do those. With the tabular method, it'll take us like 30 seconds to do the problem. It'll be beautiful. In fact, here, I'll let you get a second to absorb it. Yeah.
So what if you have f of x, like its derivative doesn't do square?
Yeah, then that's not a good f of x, and you shouldn't do this. Have you guys been finding, by the way, my PowerPoints online? I put like a Mr. Chase PowerPoints folder inside of the This Guess ones, so you can see all my slightly more professionally done. Oh, yes. I did. I had to sneak it in.
He does not have a whole
Yeah, exactly. It's really rough. I mean, we barely talk to each other.
Except for when you guys take pictures.
Oh, except for when we begrudgingly. All right. So I don't know. Let's try this method on this guy here. X cubed sine x. I'll give you a chance to do it. Why don't you write it down? I'll give you a second to write it down, and then I'll put up the other slide for those who haven't copied it or who want to look at it as you're working on it. the integral of x cubed sine x dx. Write that down. And I'm going to flip back to the other slide. And you start applying this. I think it's fairly clear what we're going to let you be in this kind of circumstance, right? Okay? Let's give it a try. Carefully obey the instructions. Yeah, so if someone asks you to evaluate an integral using integration by parts, tabular is integration by parts. You might be thinking like, can I use tabular? Yeah, this is integration by parts. It's just a way of organizing our thoughts. So the first one is positive. So the first one is positive, and then positive. All right, you have it yet? Homework 2 tonight, you guys who are leaving. See ya. Good luck. I mean, swim hard. Practice hard. Okay. So let's set up some columns here. So f of x and g of x. Here we go. X cubed, 3x squared. It's so fun. 6x, 6, and then 0. Over here we're doing sine x and antiderivatives. Negative cosine x, negative sine x. We'll put a 0 down here. Cosine and sine. Yeah? And then a plus, a minus, a plus, a minus. And then we just do a little tick, tack, toe, tick. Okay. All right, so you ready to write down? It's so refreshing that we can just write it down this quickly. Isn't it great? Negative x cubed cosine x plus minus 3x squared sine x plus 6 cosine x minus x cosine x minus 6 sine x plus c. It's actually, it might be a tall order for you to think, oh, I have to check by taking the derivative. But actually, like I said, think garbage collection here. It's really fun, actually, right? Take the derivative of this. What do you get? Negative x cubed. Oh, wait, it'll be x cubed sine x, right? Isn't the derivative of this x cubed sine x? Oh, wait, product rule. Plus negative 3x squared cosine x. Okay, but that's the derivative of this, isn't it? Isn't the derivative of this negative 3x squared cosine x? Boom, that went away. Oh, but wait, also 6x sine x. Oh, but perfect. This has the derivative of this is negative 6x sine x. So those go away. You see how each time you're collecting the garbage of the last? Try taking the derivative. I don't want to do it for you. Okay? You'll feel it the whole way through. Remember, you're taking integrals in this column over here. You're taking integrals as you go down the right column. Yes, like it. With the what?
What if you just ask the integration by parts method?
You would get the exact same thing. Absolutely. It would just take. It would take 4 applications of integration by parts. Which would work. And in fact, actually, I encourage you to try it just so you can see that in the end, this is exactly what you're doing. You know, like,
Right now, I just got
well, in your head or something? Oh, wow. All right, let's do this one. Like you said, this would be terrible. This would have taken you like 20 minutes if this was on the homework, if we hadn't had a way of quickly bookkeeping this. Whereas here, this will take you like 20 seconds, right? I think most you had to do in the homework was 2 integration by parts, right? I think you'll survive. Careful with your integrals here. What's the integral of that? Let's just do the first one together here. Yeah. Now you're on the right path. We didn't want anyone to write -2 e to the 2x, right? That would be bad.
Yes.
So what do we get here? 1/4 e to the -2x, 1-1/8 e to the -2x, 1/16. It's almost like you could write a rule for this. -1/32. All right, here we go. So we get -1/2 x to the 4th e to the -2x. Minus, x cubed e to the -2x. We'll multiply the 4 and the -4, sure. Minus 12/8. You want to simplify that? We'll write 3/2, I guess, yeah. X squared e to the -2x. Can we do it before the lines? Minus 24/16. You want to simplify that? 8. Is that 3/2 too? Right? 24/16? Yeah. X e to the -2x. And lastly, minus 24/32 is something. Is that 3/4? E to the -2x plus c. Again, quite a bit faster than having to do integration by parts 5 times, right? Which is what you have to do there. 5 times you have to do integration by parts. Again, check the derivative. It's actually kind of fun on these, right? You're well equipped to do homework 2, and I love you all.